Hello everybody and welcome to our video on section 15H, second and higher derivatives. So since the derivative of a function is itself a function, we can take its derivative as well. So in other words, we can take the derivative of a derivative. The result is called the second derivative and is denoted by f double prime of x, or d squared y by dx squared. So for example, if I wanted to take the second derivative of the function x to the 6, the first derivative would be 6x to the 5. I would drop the exponent 6, keep the x, and reduce the exponent by 1. Then the second derivative, I would take the derivative of the derivative. So I would bring out that 6, drop the 5, keep the x, reduce the exponent by 1, and multiply those two factors together. Okay. I could also find the derivative, the second derivative for a slightly more complex function. So here I need to apply the sum rule as well as the constant multiple and product and power rules. So I would take the derivative of 5x squared, which would be 5 times 2x, and the derivative of root x, which would be 1/2 x to the negative 1/2. Now normally I would want to rewrite that with a radical symbol, but because I'm going to take the derivative again, I'm going to leave it in its exponential form. So I'm going to take the derivative of 10x, or 5 times 2x, and get 5 times 2. And I'm going to take the derivative of this part. I'm going to factor out that 1/2, drop the negative 1/2 exponent, keep the x, and reduce the exponent by 1 again. Remember, that's like subtracting 2 over 2 from negative 1 over 2. Simplifying that, I get 10 minus 1/4 x to the negative 3/2. And then I could rewrite that in radical form, bringing the x to the denominator to account for the negative exponent and taking radical x cubed. Okay, I can stop here if I like, or I could go one extra step, but this is fine. Okay, and now you might be thinking, if I can take a second derivative, can I take a third derivative or a fourth derivative? And that is true. You can keep taking as many derivatives as you want. You just keep differentiating the last derivative that you got. We use a notation that looks like this. Instead of writing a whole bunch of primes at the top, we use brackets with a little number there. Or we use this, the numbers in where we had the 2 in our dy by dx notation for the nth derivative. So for example, if I wanted to take this function and find f at 2, so f at 2 just means plug 2 in for x. No derivative required. That is 2 cubed minus 2 times 2 plus 5, or 9. Now I want to find f prime at 2. I'm going to take the derivative, which is going to give me 3x squared minus 2. And then I'm going to plug in 2 for x. And I'm going to get 10. If I want to take the second derivative and evaluate it at 2, the second derivative is 6x. I go back to my first derivative, take the derivative of that, which is going to be 3 times 2x, or just 6x. And then I'm going to evaluate it at 2, so I'm going to plug in 2 for x and get 12. And if I want to evaluate the third derivative, I would take the derivative of 6x, which is just 6. And if I try to plug in 2 now, I can't. The answer to this function is always 6. Okay? So that's kind of a bit of a tricky question. You might be wondering, why do we do higher order derivatives? Well, we'll do them a lot as we do some applications of derivatives in a few weeks. But remember that derivatives are useful to determine the rate of change. Velocity is the rate of change of displacement at a specific point in time. So velocity is the first derivative of the position function. And acceleration is the rate of change of velocity with respect to time. So acceleration is the first derivative of the velocity function, and it's the second derivative of the position function. Thank you and have a great day. Stay safe.